of fractions.
All right, we are recording, just so you know.
Hi, Diego.
Hey, Diego. People in the future, when they're doing this, will be like, "Who the hell is Diego?"
That's right.
We should continually refer to Diego throughout the entire course. So, like, in later years, like 10 years from now, everyone will be like, "Who's Diego?"
Right.
Make up some name for that.
Yeah.
Just good.
So my general comment here is one of the differences between astrophysics and physics is astrophysics is interested in natural history. So it's kind of like paleontology in that regard, in that we'll be studying the history of the universe, history of the Milky Way, how stars are born, and how they die, and stuff like that. As opposed to, here's the laws of physics, let's explore the consequences of the laws of physics. And as such, on the exams, some of the problems will be like you would have like for E&M, where apply the physics to this problem, but some of them will be, tell me a story, so to speak. In other words, explain to me in words how this works. Because also I think it's important to develop your astrophysical intuition, so to speak, too. So I will have regular kind of physics-y problems, you know, where you use equations and all that kind of stuff, but there will also be some, tell me about the stages of a star's life, things like that, where it's more, not qualitative, but you have to be able to explain it in words. Anyway, let's begin with chapter 2 from Bob, the big orange book, the textbook. And that is the one about celestial mechanics. Let me get good lighting on here. I hope the resolution's high enough for Diego to see everything clearly.
Lego my Diego.
Lego. Yeah, well, that bank is out. Okay. Anyway, also I will, just like I do for E&M, I will put my lecture notes on Blackboard. I'm not there yet, but they will be shortly. Sometimes you will note, and sometimes I'll deviate from them. Sometimes you will notice I've changed some of them, these places where they occur, but some of these lecture notes are old enough that they're based on stuff in the first edition of the book, which use CGS units rather than SI units. And so, like for example, here I have that the gravitation constant is 6.67 times 10 to the minus 8 dynes per centimeter squared per grams to the minus 2, as opposed to kilogram, Newton meter squared per kilogram squared. And I'll try to remember to put them in SI. The reason is that astronomers, astrophysicists who do theoretical calculations often use CGS units. It turns out there are some advantages to CGS units from a theoretical standpoint. But on the other hand, the authors changed that in the second edition of the book because they realized that undergrads to whom the book is targeted typically use engineering units, SI units. They don't have an intuition for CGS units. And so now the book now uses SI units. But sometimes, and sometimes I've erased and filled in the SI units in my notes, but sometimes not. So just be aware of that if you're looking at the online notes. Anyway, let's talk about celestial mechanics, shall we? Yes, we shall. Have you guys had mechanics yet, as in Physics 310? You don't have to have had, but yeah, so it kind of, it doesn't affect how I teach this, but it might affect whether I mention Lagrangian or not, and say, oh, by the way, this is Lagrangian, but we're not going to be using Lagrangian here. Have you had one? You have? Yeah. Okay, right. And I don't think Diego has either.
No, you took
Yeah. Oh, he took mechanics. Oh, okay, okay. Oh, sorry, Diego. I didn't mean to assume you didn't have mechanics. All right. Anyway, Kepler's laws. So these are named after Johannes Kepler, who formulated them in the early 1600s. Let me bring up the slides. It's worth saying something about which I'll put the slides on Blackboard too. It's worth saying something about these Control-Alt-Delete. Control-Alt-Delete. There we go.
Fizzline.
Password is dot, 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 as you can see. Let's write that down, that's right, you can see everything.
That would be amazing.
Yes.
Wonderful.
Mhm. No, I could not reconnect all the network drives. Hold on,
Yeah.
I don't need all the network drives.
Is this still set to default in German?
I'm bringing up Opera to avoid any issues of that,
Okay.
or it now being Dr. Treese's account or anything like that. Yeah, so let's see.
Crash was gross. I'm still trying to finish the basics and
Apparently I'm logged in.
How many are there?
There's like 40, 100, something like that.
Yeah, there's like 41, 42 of them, something like that. Yeah, it's kind of like, it's astronomy 110, 111, all
Yeah.
on video lectures. It's essentially at exactly the same level as astronomy 110, 111 are. And in fact, it's worth watching those videos.
I think
Because
I'm
it,
like
yeah.
33, something like that.
Yeah, it's worth watching them even though you're doing things at a more advanced level. It gives you the big picture, you know, and he has better special effects than I do. So,
It's got a higher production budget.
he's got a much higher production budget than I do, that's right. All right, I'm going to go into Drive. What is this thing set at in terms of, it's like some weird resolution. I'm going to have to play with the font settings apparently. But I'll just
Did I go
go
to
to
the trash?
What's that?
Did you move in? I looked to the trash.
Did they do that? No, it wasn't very nice, and he wasn't.
Here's
Let's
the
see.
entire extra folder.
Yeah. Courses. And I think I just, do I call it Astronomy 310? I guess I do. And 2017 fall. And this is a lie right now, shared with students. I haven't done it yet.
Yeah.
But here's all the lecture notes. And here is the Google Slides presentation for Chapter 2. Here we go. Yes. So Johannes Kepler worked with this gentleman, Tycho Brahe. What? No, I'm not trying to share it. I mean, I will, but not yet. I know I hit the wrong thing. Present. That's what I meant to do. There we go. Okay. So, oh boy, that's just burning out. How can Diego ever see this with so much light on it?
I'll have to imagine.
Yes. Okay, there we have Tycho Brahe, who lived from 1546 to 1601. He was the, if you will, well, I guess I shouldn't say the greatest naked eye astronomer necessarily, but he constructed the most sophisticated naked eye instruments that were ever constructed. And then shortly thereafter, this thing called the telescope came into wide use. But he was just a little pre-telescopic, as it were, as actually the telescope was invented right around the time that he was born, but he never used a telescope astronomically. Of course, Galileo was the first person to do that and widely publicize the fact that he had done that. Even Galileo wasn't the first person to turn a telescope towards the heavens, but he was the first person to really do that and make other people take note of it. But anyway, Tycho Brahe, shown here, hired an assistant, Johannes Kepler, and Johannes Kepler was trying to understand the orbits of the planets, and unlike Tycho, Kepler was a Copernican. He accepted the Copernican idea that the sun was at the center of the solar system. And Tycho had made these very precise for the time observations of the position of Mars. And assuming combinations of circles being the orbits, as had been believed up to that time, even by Copernicus himself, Kepler was unable to precisely reproduce Tycho's observations. There was an error as large as, I believe, 4 minutes of arc. So about a 15th of a degree, about 1/8 the size of the full moon on the sky. Kepler could have written it off saying, well, it's just observational error, but he knew how good an astronomer Tycho was, how precise his measurements were, and he knew that his precision was better than 4 minutes of arc. And so he figured that what this was indicating was that the orbits of the planets were not, in fact, combinations of circles. And so he was trying to figure out what might explain it. Legend has it that a relative was a winemaker who used elliptical casks to store the wine, and that made him hit on the idea that the orbits of planets are, in fact, ellipses. And when he adopted that notion and formulated 3 laws based on it, he was, in fact, able to successfully reproduce Tycho's observations of Mars. Label these sometime, anyway. And so he formulated his famous 3 laws of planetary motion, which also apply to binary star systems and other phenomena. So Kepler's laws, finally. Law number 1. Yeah, we need to get that bank fixed because it's not bright enough here. Anyway, Kepler's first law, which was published in a book that he wrote called Astronomica Nova, which would be what in English? What's nova? New. Yeah, so the new astronomy, Astronomica Nova, which he published in 1609. And we'll explain in more detail what each of these is saying after I write all 3 of them down. His first law is that a planet orbits the sun on an ellipse. With the sun at one focus of the ellipse. So that's his first law. Planets orbit the sun on ellipses, and the sun is at one focus of the ellipse. Heretical idea, because the idea before had been that the heavens were perfect and the circle is the most perfect shape, and therefore planets should orbit on the most perfect shape, which would be a circle. So they had these elaborate combinations of circles on circles in order to try to explain the planetary motions. And you do a pretty good job with it, but on the other hand, it turns out that an ellipse does a better job. Second law, also from Astronomica Nova. Astronomica Nova. The line joining a planet to the sun sweeps out equal areas in equal times. The line connecting a planet to the sun sweeps out equal areas in equal times. So that's why this is also called the law of equal areas. But of course, it's important to realize that the equal times are in there too. Sometimes students get confused and think that the law is simplified to the line connecting a planet to the sun always sweeps out the same area. No. In 1 week, it sweeps out more area than it does in 1 millisecond. So if the times are unequal, the areas are unequal, but if the times are equal, the areas are equal. And the third law, which was from a different book. It took him 10 more years to publish that one. That one's from Harmonica Mundi. I think that would translate to like the harmony of the world, of the worlds. (1619). Mathematically, that says p squared is equal to a cubed. Where p is the orbital period. And Earth years, A is the semi-major axis in astronomical units. AU AU is the semi-major axis of Earth's orbit. So it's done in terms of Earth quantities, although it would work for any planet. You could also use Mars years and Mars astronomical units, if you will. Use Mars as the basis. But we live on Earth, so we use it as the basis. So that's how I'll write it, as opposed to you could do a long form along the lines of the square of the orbital period of the planet is directly proportional to the cube of its semi-major axis of its orbit. Well, that's p squared equals a cubed. In general, it would be p squared is k times a cubed, where k is the constant of proportionality. But if we use Earth, then we can see that k has to be 1, because in general it would be p squared is some constant times a cubed. But in these units, what is Earth's orbital period? In terms of Earth's orbital period is equal to 1, right? And in terms of Earth's semi-major axis, the A, which is the semi-major axis of Earth's orbit, but we'll say more about what semi-major axis is later, but given that we're using Earth as the reference, in terms of astronomical units, Earth's semi-major axis is equal to 1. So 1 squared is some constant of proportionality times 1 cubed. Solve for k in those units.
Definitely 5.
It's definitely 5, yes. So therefore, k is 5/5. You are off by a factor of 5, which simplifies to 1.
This is one of those times where I feel so dumb.
Yeah. So in those units, p squared is a cubed. We'll see that if you use like SI units, then p squared is 4 pi squared, or what is it? It's whatever. 4 pi squared over g times the sum of the masses. You know, it's different in SI units. But in these units, k just simplifies to be 1. So, what's that?
I was just looking at the point k equals 5/5.
Yeah, well, you said 5, so I figured out correctly.
Some more you would guess what.
Ready? Yep. So, so let's say more about what all this stuff is about. So ellipses. What's an ellipse? So an ellipse is it's a locus of points, a set of points, such that the sum of the distances from 2 fixed points called the foci is the same for every point on the ellipse. So here's a generic ellipse here, and an ellipse, unlike a circle, has a long axis called the major axis and a short axis called the minor axis. And half the length of the major axis is the semi-major axis. Half the length of the minor axis is the semi-minor axis. And along the major axis are 2 points called the foci. The plural of focus is foci. I have a forward focus. If I park it next to another one, there are 2 forward foci there. It turns out that forward focus owners who care enough to join online message boards and stuff like that do in fact refer to them as foci in the plural. It's not 2 forward focuses, it is in fact 2 forward foci, because apparently focus owners like me are an intelligent lot that uses the proper plural for focus when referring to multiple copies of them. And the idea is that, you know, for a circle is a locus of points where they're all the same distance from a fixed point called the center. An ellipse generalizes that idea. Now there are 2 fixed points, and it's the sum of the distances from the 2 fixed points that stays constant for every point on the ellipse. So you can actually draw an ellipse by using a string and a pair of thumbtacks and a pencil. You stretch the string taut, and if you think about it, as you move the pencil, keeping the string taut at all times, it will always be true because the length of the string stays fixed, because it won't let you stretch it. Don't use a rubber band for this. Because the length of the string stays fixed, and because the distance of this arc, of this length of string between the 2 foci isn't changing, that the total distance from one tack along the string to the pencil back to the other tack, that stays constant as you move the pencil around. So you will automatically trace out an ellipse if you create this contraption and move the pencil around. And so that's how you physically draw an ellipse. And so clearly, the shape and size of the ellipse is going to be controlled by how far apart you put the thumbtacks and by how long you make the string. And you can draw ellipses of arbitrary size and shape that way. And there's another parameter, which we'll define in a little more detail momentarily, called the eccentricity, which describes how flattened the ellipse is compared to a circle. So a circle note is an ellipse, and it's an ellipse where the 2 foci coincide with one another. And we say that in that case, the eccentricity is 0. And as the eccentricity increases, we'll give the exact definition in a minute, the foci become further and further apart compared to the length of the semi-major axis, and the ellipse becomes more and more flattened. So that's like a qualitative overview of what an ellipse is, and now we'll be more quantitative about it. Any questions at this point? Okay, then let's proceed, shall we? Just going to double check that it's still recording since this is the first time. Diego, are you still there? Oh, good, you are.
Some student in the future is going to be like kind of dozing off when they see that comes in, and it's going to get loud all of a sudden.
Yes, that's right.
Checking up on them.
I should be more good at that. Insert student name here. Are you still there? And now for our musical number. Yeah.
Have a halftime show.
That's right. Yeah. Well, it'll be like,
Yeah, we can monetize this video and have ads during.
yeah, that's right. Yes. Today's class is brought to you by Orbit. Orbit gum. See what I did there? Eclipse gum, that's right, yes. Yes. Okay, so I will draw a generic looking ellipse here. I won't try to be precise about it. And, well, I should try to make the semi-major axis be the line on the board here. Let's try not to suck, shall I? And no, it's not too. Let's see. Okay, that's good enough. F and F prime. So there is the minor axis. I'm letting that line, the seam between the boards, be the major axis of my ellipse there. And A is the symbol we use for the length of the semi-major axis, but people get sloppy and they use the words semi-major axis interchangeably. Well, they use it to mean both the actual semi-major axis, one of the two half-axes, and the length of that said thing. So you have to just get it from the context how to mean that. So A is the semi-major axis. Really, it's the length of the semi-major axis, but again, people get sloppy and they just say A is the semi-major axis. There's really two semi-major axes. And B is the semi-minor axis. The definition of the eccentricity is that the distance from the middle of the ellipse to either focus is A times the eccentricity. So the distance, the distance between the two foci, another way to put it, is 2AE, where E is the eccentricity. And 0 is less than or equal to E is less than 1 for an ellipse. As we'll see, there are other so-called conic sections where E is 1 or greater than 1. For an ellipse, E lies between 0 and 1. And the lower limit is included. 0 can be E, but 1 really actually turns it into a parabola, it turns out. So if E were equal to 0, then both foci would be 0 away from the center of the ellipse. In other words, the two foci would coincide, and you would have a circle. A circle is an ellipse where the two foci coincide.
I said every circle is an ellipse, but not every ellipse is a circle.
That's absolutely right, yes. Every circle is an ellipse, but not every ellipse is a circle. Correct.
Square.
Yes, every square is a rectangle, but not every rectangle is a square. Every human is a primate, but not every primate is a human. We could just do this all day.
Every ship is a boat, and every boat is a ship.
There you go. Yes. Speaking of animals, one little fun thing, well, fun for me during the eclipse is my wife got bitten by mosquitoes around the time of totality because they got confused and said, "Oh, it's time for our evening vampire reading." And so how they came to bite people during totality. And a little bit before. So that angle right there, we're going to call that theta. There's some point on the ellipse, and we will call the distance from focus F to generic point P on our ellipse R, and focus F prime's distance to P will be R prime. So note that we can say the equation of the ellipse is r plus r prime is 2 times a. In other words, the sum of those distances is constant, and in fact it is twice the semi-major axis. And the reason we can say that is it's the same for all points on the ellipse. Well, there's one particular place where it's easy to evaluate, namely on either end of the ellipse, for the points on either end of the ellipse, then notice that the total length is 2a, because if you think of the string again, in going from F to that end of the ellipse, you go that far, and then that's the same distance as over here by symmetry. And so the other piece, the rest of the string, goes from F prime to the end of the ellipse. And so if you add F prime to the end of the ellipse plus F to the end of the ellipse, well, F to the end of the ellipse is the same as this over here. So the total length of string is twice the semi-major axis, or in other words, it's the length of the major axis. So since the distance is the same, the sum of the distance is the same everywhere around the ellipse, and on either end of the ellipse it's equal to 2a, it's 2a wherever you are along the ellipse. So the length of the string is twice the semi-major axis, or in other words, it's the length of the major axis. So this expresses the fact that the sum of the distances from the foci is constant. So now, consider the following. Consider a point on either end of the semi-minor axis. Where r equals r prime equals a. So if I draw a picture of that, let's say that end of the semi-minor axis, in that case by symmetry, r prime and r equal to one another, and they both must be equal to a because their sum is 2a, and so a plus a would be 2a. So that's the idea here. So they're both equal to a. Well, now we've got a pair of right triangles there, and remember that by definition, either focus is a distance AE, where E is the eccentricity from the center. And we know that the semi-minor axis, that length we call B. And so we've got a right triangle whose hypotenuse is A and whose sides are B and AE. So we can use the Pythagorean theorem. Pythagorean theorem says that that a squared is equal to b squared plus a squared e squared. Hypotenuse squared is some of the squares of the sides. So a squared is b squared plus a squared e squared, which we're deriving for this point, but again, it's true. We're finding something that's just true generically about the ellipse by doing this. A squared is b squared plus a squared e squared. Or in other words, b squared is equal to a squared times 1 minus e squared. That formula is box-worthy. B squared is a squared times 1 minus quantity 1 minus e squared. So if you know any two of A, B, and E, that formula tells you the other one. That formula, or some transposition of it, some rearrangement of it. Note that E equals 0 implies B squared equals A squared, or in other words, B is equal to A. E equals 0 implies B equals A, and that would mean that the shape is a circle because both axes are the same length. For a circle, every axis through the center of the circle is both a major axis and a minor axis because they're all the same. And what do we call the semi-major axis of a circle? We call it its radius. Yeah, so a circle is an ellipse, right, with eccentricity 0, and its radius is equal to the semi-major axis in that case. So that gives us a circle, as we would expect. As E approaches 1, B is going to approach 0. So the ellipse degenerates towards a straight line segment. Although, as we'll see, E equals 1 itself, actually, we use that to define a parabola, as a matter of fact. It doesn't directly follow from anything we've said, but there's a more generic formula for conic sections that putting in E equals 1 yields a parabola. All right, seems like a decent spot to take our break. Yes?
Just a quick question. Maybe if it's geometry, or why do ellipses have two foci?
It's a definition. So in other words, the definition of an ellipse is that it is a locus of points such that the sum of two distances, such that the sum of the distances of each point from two fixed points called the foci is constant. So the reason why ellipses have two foci is no different from the reason why circles have one center. In other words, it's just the definition of the shape. The very definition of the shape demands that it's something you construct using two foci.
Oh.